In this talk, I will be talking about multi-pass graph streaming lower bounds for cycle counting, max cut, meshing size, and other problems. This is a joint work with Sepehr, Assadi, Gillat, and Raghuvansh, Saxena. In this paper, we study graph problems in the streaming setting, and more specifically, the input graph is a graph with n nodes, and it is presented as a sequence of edges or stream of edges, such that an algorithm tries to solve graph problems using limited memory by making one or few passes of the stream. And the important parameters in this setting are the number of passes and the space usage, how many passes the algorithm makes and how many bits of memory it uses. This is also sometimes called the insertion-only model, as one can view the stream as a sequence of edge insertions to an initially empty graph, and the input is simply the graph after all insertions. And then there are two main areas in this setting. One is the semi-streaming setting, where we try to design algorithms using n polylog n space for problems on possibly dense graphs. For example, finding the minimum spanning tree, finding large matchings, and spanners. And in this setting, in this case, the output size is often superlinear, or even n polylog n. And the goal here is to use polylog n space per vertex. And we want to compress the edge space. In other words, how do we solve the problem without storing the entire, possibly dense graph? And the other area is the graph streaming, where we want to design algorithms using polylog space for estimating properties of the graph. For example, estimating what is the max cut value, what is the max matching size, and so on. And in this case, the output is often a number, or it's even a decision problem. Output is just one bit, and the goal is to compress the vertex space. In other words, how do we solve the problem without storing something about every vertex? And I would like to emphasize here that these two areas are usually quite different in both upper bounds and lower bounds. And in this paper, we'll focus on the second area, the graph streaming. And already spoiled in the title, we'll be focusing on the lower bounds on the passes and space. And in this context, it would mean that the algorithm either makes that many passes, or it has to use at least super polylog space for some problem. And the problem we study in this paper, or actually a class of problems, is the following. We'll study the problem of deciding if a given graph G consists of many short cycles or a few long cycles. And the precise definition of this problem actually depends on the definition of many short and a few and long. But intuitively, when the gap between many and few and the gap between short and long is smaller, the problem becomes harder, because as these two cases become closer, and it's easier for us to prove a lower bound. And in fact, one such example is identified by Verbin and Yu in 2011. They defined this problem called gap cycle counting, where there's a constant factor between these two cases. The problem asks to decide if the input graph G is a disjoint union of k cycles or a disjoint union of 2k cycles, the cycles of length k or cycles of length 2k. And they also prove a lower bound for this problem. They prove that any one-pass streaming algorithm must use space at least n to the 1 minus 1 over k to decide this. Before we get into the details of these problems, let's first briefly recap how streaming lower bounds are usually proved. I guess one of the most common way to prove streaming lower bounds is by reducing from the communication problems. And this is also the approach that we take in this paper. Suppose this is a data stream with m elements in the stream, and in our setting, each element will correspond to one edge in the graph. And we define the following communication game between two players, Alice and Bob. So first, Alice gets half of these edges, and Bob gets the other half. And their goal is to solve the same graph problem by sending a few short messages to each other. And suppose that there is a good streaming algorithm on this data stream, then the players can simulate this algorithm in turn by sending the memory. For example, Alice can first simulate this streaming algorithm on first half of the stream, and then send the memory to Bob, and then Bob continues the simulation, and maybe send it back to Alice after the simulation. So if there's a streaming algorithm using p-pass and c bits of memory, then this gives us a communication protocol using 2p-1 messages of c bits. So in order to prove a streaming lower bound, it suffices to prove a lower bound for this two-party communication game. And the lower bound of gap cycle counting is also proved via reduction from some communication problem that is hard for one-way communication. And this problem is called Boolean hidden hypermatching. The actual definition of this problem is not crucial for this talk, but I want to mention that gap cycle counting and BHH are very useful intermediate problems for proving one-pass streaming lower bounds. And people have used them to prove lower bounds for approximate max cut and approx max matching and approx MST weight and so on. But one crucial problem with this approach is that this BHH problem is actually easy for more than one round of communication. It turns out that there's a protocol using polylog M communication in just 2 rounds. And for this reason, even a 2-round lower bound for gap cycle counting is not known. So are the lower bounds for many other problems that are reduced from them. And the main contribution of this paper is that we proved multi-pass lower bounds for all these problems. And the concrete communication problem we study in this paper is what we call one or many cycles problem. In this problem, the input consists of 2 disjoint perfect matchings, MA and NB, on n vertices. And Alice is giving the first matching MA, and Bob is giving the second matching NB. And the input graph G is simply the union of these 2 matchings. And because these 2 matchings are both perfect and they are disjoint, so G is guaranteed to be a true regular graph. But further, we promise that this graph G is either a length n Hamiltonian cycle, which is a yes case, or it is a disjoint union of n over k length k cycles for some parameter k, and this is the no case. And the goal of the communication game is to decide whether we are in the yes case or in the no case. So intuitively, this is a very large gap. For constant k, this is probably the largest possible gap between many short cycles and a few long cycles. So intuitively, this would mean that it's easy for algorithms and making our lower bound stronger. So formally, we prove the following theorem for this communication problem. We prove that any R-round communication protocol distinguishing yes and no must send at least n to the 1 minus k to the 1 minus over r bits. Okay, let's see what this means. So suppose the number of rounds r is log of log k. Then the quantity in the exponent k to the minus 1 over r is a subconstant. That means the communication lower bound we prove is about n. So that means either the communication protocol uses at least log k rounds of communication, or the cost is at least n to some constant. And our proof also extends to distinguishing between k cycles and 2k cycles, the gap cycle counting problem we mentioned earlier, and with the same parameters. And by setting r equal to 1, this recovers the previous lower bound, as the lower bound would just be n to the 1 minus 1 over k. Okay, now let's see what does our communication lower bound imply for the streaming algorithms. What streaming lower bounds do we give? So I guess the most straightforward example is the same problem, giving a graph G and with promise that it's even a Hamiltonian cycle or it's a disjoint union of cycles of length k. And distinguishing yes and no, we prove that it must take either log k passes or n to the some constant space by using the reduction from communication problems to streaming algorithm. And it's worth noting that the naive reduction actually requires k in this case to be even, because otherwise in the no case we won't be able to write this graph, decompose this graph into 2 disjoint perfect matchings. But it turns out that there's a trick we can do directly to the hard instance, and it allows us to prove the lower bound directly for all k that is at least sufficiently large constant. And using this streaming lower bound, we can prove lower bound for other streaming problems. For example, approximate max cut, and let k be an even number. And suppose we're in an yes case, then the max cut size of a Hamiltonian cycle is roughly n. We can put almost all the edges in the cut. But in the no case, the max cut will be roughly 1 minus 1 over k times n, because each short cycle has odd length, and we have to lose at least 1 edge from each cycle in the cut. and this creates a gap of 1 minus 1 over k, and by setting k to be 1 over epsilon, this gives us a lower bound for 1 plus minus epsilon approximate max cut. It either has to use log 1 over epsilon passes, or the space has to be n to some constant. And similarly, we prove that for 1 plus minus approximate max matching, either it has to use log 1 over epsilon passes or n to some constant space for the same reason. And in the rest of this talk, I'll give an overview of our proof strategy. Okay, to facilitate the analysis, the instance we focus on is a layered graph with k layers, and each layer has a fixed set of vertices. And there's a perfect matching between any two adjacent layers. And further, we're going to add an identity matching between the first and the last layers. Namely, we add an edge between the ith vertex in the first layer and the ith vertex in the last layer. And then Alice will get all the odd matchings and Bob will get all the even matchings. So it is not very hard to see that both players in this case will get a perfect matching, and these two matchings will be disjoint from each other. And in the Huacheng instance, in this instance, the only part that is not fixed is the k-1 matchings in the middle. And for those matchings, we further require that the top half of the first layer will match to the top half of the last layer using the edges in the middle. And because every layer has a matching, this also means that the bottom half of the first layer matches to the bottom half of the last layer as well. Okay, next let's see why this instance is related to distinguishing between Hamiltonian cycles and k cycles. Okay, first let's suppose that the matching between these two yellow dashed boxes, the top half of the first layer and the top half of the last layer, is the identity matching, meaning that the ith vertex in the first layer through the k-1 edges in the middle will connect to the ith vertex in the last layer. In this case, actually all these yellow edges that connect them will form a disjoint union of k cycles. It's because the ith vertex will connect to the ith vertex in the last layer, which connects back to itself using the identity matching we added. And all these this forms a k cycle, and all these k cycles will be disjoint. And now suppose that the matching between these two boxes is actually a +1 matching, meaning that the ith vertex in the first layer actually connects to the i+1th vertex in the last layer through the edges in the middle. And in this case, all these yellow edges will actually form one big cycle, because the first vertex in the first layer connects to the second vertex in the last layer, which connects back to the second vertex in the first layer, and so on. So everything will be connected in the top half. And what we actually prove is a lower bound for distinguishing between the matchings being either identity or the +1 matching. And the graph in these two cases will roughly correspond to the graph, the two cases that we wanted to distinguish, except for the edges that connect the bottom halves, which we call the noises. But it turns out that there's a way to post-process the graph so that the noises can be completely removed, and the graph becomes simply a big cycle or n over k cycles. But for technical reasons, we will have to need this noise to get the lower bound. And also I would like to mention that there's actually nothing special about these two matchings, the identity or +1, in terms of lower bounds. And the lower bound proof actually works for any two matchings, and therefore by replacing this +1 matching with the XOR 1 matching, which makes the graph a disjoint union of two k cycles, we will actually prove the same lower bound for k cycles versus 2k cycles, as we mentioned earlier. Okay, so for now, for simplicity, let's forget about the noise, and let's just think the algorithms trying to figure out what the final matching is, what the matching between the first layer and the last layer is through the middle k-1 matchings. And set our goal to proving the following statement, proving that any little of log k round n to little of 1 bit protocol learns almost nothing about the final matching, the matching between first and last layer, as a demonstration of the idea. The proof consists of two steps. First, we'll prove a one-round lower bound, and then we apply this one-round lower bound, and we apply a round elimination argument to eliminate the number of rounds one at a time, to extend the lower bound to multiple rounds. So formally, in the first step, we'll prove the following lemma. Prove that for graphs with C layers, for some sufficiently large C, any one round entry little of 1-bit protocol learns very little information about the final matching. So then we use this lemma to get the final statement. So roughly speaking, we prove the communication lower bound in the first step, and then we prove the round or the pass lower bound in the second step. So now let's first see how do we get the pass lower bound, the log k pass lower bound, assuming we have this lemma. Okay, so giving a graph with k layers, that's our input graph, and the main idea is that we're going to divide these layers into blocks of size c, and then we apply the lemma from first step, this one round lemma, to each of these blocks. So for example, this allows us to show that after the first message of the communication, for each of these blocks, the players learn almost nothing about the matchings within the block. Therefore, we can view the rest of the protocol as a protocol with one fewer round, but solving an instance with k over c layers. So basically, after one message, the players learn almost nothing about the k over c block matchings, and then we are going to view the input, the new input, as k over c matchings over the blocks, and then give the odd block matchings to Bob, and give the even block matchings to Alice. And in particular, by the one round lower bound that we assumed, Alice doesn't know Bob's block matchings, and Bob doesn't know Alice's block matchings. And by continuing the protocol, if the players could figure out what the final matching is, they essentially solve the same problem on k over c layers, but with one fewer round. And then we're going to set c to be a large constant, and then if the number of rounds is little of log k, then we are going to apply this argument not many rounds, and we are left with a non-trivial problem with no rounds of communication. And this leads to a contradiction. And this is how we get the log k pass lower. Okay, next let's see how to prove the one round lower bound, which will actually give the communication lower bound. So we first prove that for any fixed vertex S in the first layer, any such protocol learns almost nothing about where S connects to the last layer, this question mark vertex in this picture. So this is essentially a one round small advantage version of the pointer chasing lower bound. So standard pointer chasing question studies exactly this problem with probably less than c minus 1 rounds. And the classic result states that in this case, if the communication is low, then the players have a large error probability in predicting the question mark vertex in the last layer. And we restrict the number of rounds to 1 round. This is a much stronger restriction, but we also prove a much stronger consequence. Not only is the error probability large, but the players almost have no idea about where this question mark vertex is. Even the distribution in Bob's view after the communication is very, very close to the uniform distribution. And intuitively, this is true because Alice doesn't know all these red edges that connects S to the last layer, but she has to send information about her input to Bob in order to solve the problem. So if she does random sampling, then random sampling hits each of these red edges with probability n to the minus some constant in each layer. But Alice has roughly c over 2 layers to send, so the probability that the random sampling hits all these layers is roughly n to the minus c. And we show that in general, for any protocol, not necessarily random sampling, this bound is still true. Then we extend this result to the following. We show that even conditioned on where a subset of vertices in the first layer, S1, S2, where they are matched to the last layer, then the lower bound, the same lower bound, also holds for the next S. So this means that first, by the step 1a, we show that Bob, after the communication, Bob doesn't know who vertex 1 is matched to. Then conditioned on who vertex 1 is matched to by step 1b, Bob doesn't know who vertex 2 is matched to. Then conditional on where the first 2 vertices are matched to in the last layer, Bob doesn't know where the third vertex is matched to, and so on. And we apply a chain rule and conclude that Bob learns almost nothing about the final matching. So this allows us to prove the one round lower bound. And then by applying the round elimination argument we had earlier, this allows us to prove the communication lower bound. And to distinguish between an Hamiltonian cycle and n over k cycles, any streaming algorithm must use either log k passes or enter some constant space. But for upper bounds, the trivial way to solve it uses k passes by simply starting from an arbitrary vertex and following the edges in one direction using for k steps using k at most k passes, and then check whether after k steps it goes back to itself or it reaches some other vertex. And this uses polylog n space and k passes. So one concrete open question is whether we can close this gap and whether in particular whether we can improve the number of passes to omega of k. And thank you for listening.